Hello chemists, this is Ms. Placino and you're watching Screencast 1.3 on measurements and density. In today's lesson we're going to learn about how measurements are evaluated, and we're going to do that through a study of density. In class today we started with a demonstration, and it's described in the Do Now. A can of regular Coke and a can of Diet Coke are placed in a large beaker of water. What will happen to each of the cans? Explain your answer. Alright, so if you were in class today, I don't want to keep you in suspense. When you take those two soda cans and you place them in water, this is what you're going to end up observing. Your red Coca-Cola can is going to sink to the bottom, and if you look carefully, the very top of the Diet Coke can is just above the surface level of the water, so it is floating. And we discussed in class, really, there's a lot of similarities between Coke and Diet Coke. They're mostly water, they have the same artificial coloring, the same artificial flavoring, but the big difference between the diet and the regular version of the soda is sugar. You have a lot of sugar in Coca-Cola, usually about 40 grams or so. And your diet sodas, whether it's Diet Coke or Diet anything else, uses artificial sweeteners, which are thousands of times sweeter than sugar, so trace amounts are added to the soda. So some students came to the conclusion that, okay, the Coke can must be heavier than the Diet Coke can. While I understand what you're trying to say, be a little bit more careful about how you choose your words. The reason we see Coke sinking and Diet Coke floating, it's not because of mass, it's because of density. So density is a measure of how much matter is in a given space. So if we look at this picture, we've got a cube and we've crammed tons and tons of, I don't know if you want to think of those as atoms or molecules, lots of particles squeezed into that cube. The more stuff we put into the cube, the greater the density is going to be. And of course, the more of those particles we remove from the cube, the lower the density would be. Something like a solid, you see a lot of particles packed into a given volume. High density gases have large amounts of space in between the molecules or the particles, so you're going to see a very low density. In today's lesson, we're going to be calculating density a couple of times. We'll use this formula. Density is equal to mass over volume. You can use any unit of mass and volume that you wish, but for this class, we're going to be using grams per either milliliter or cubic centimeter. Now, a milliliter and a cubic centimeter are equal to one another. They're expressing the same exact amount of volume. They're just two different units that we could use. Milliliter is most helpful if we're talking about something that is a liquid or an irregularly shaped object, and we can find the volume through like water displacement. Centimeters cubed is used more frequently when you have a regularly shaped solid, and you can do the length times width times height calculation to find a volume. But again, don't get really hung up on milliliters or centimeters cubed. They are expressing the same exact amount of space. Before we move on from density, just to give you another way to think about it, I want to talk a little bit about how it's probably come up in a social studies class. I'm talking about population density. Population density is usually measured in people per square mile. So I want to have you visualize two very, very different places. One you're familiar with, especially if you're one of my students, New York City. The other one you might not have visited just yet, Nebraska. So if you come in rush hour, you know how crowded New York City can be. I think based on this sign, we're looking at the 456 train over at Grand Central Station. Crazy crowded, people on top of people on top of people. I haven't been to Nebraska yet, but when I picture Nebraska, I picture lots of open, empty space and very few people living there. Drastically different from New York City. So in both cases, we look at population density in terms of people per square mile. And I think it's safe to say that no matter where you are in New York City, you're going to end up with a much higher population density than virtually any place in Nebraska. So you're looking at the same volume, I guess in this case more like area, square mile. You're measuring the same numerator, people, but New York City has a much greater population density than a less populated state like Nebraska. Anyway, let's get back to chemistry. So in class, it wasn't enough just to observe that the Coke and the Diet Coke have different densities. We want to support that quantitatively as well. In other words, we want to take measurements and support our observations with numbers. So there's no instrument in the lab where you can just take your sample, place it on it, and it's going to spit out the density. Density is a derived unit, meaning you're going to have to take multiple measurements. And based on the formula we just talked about a couple of slides ago, hopefully you know that we're going to have to measure the volume and measure the mass of our samples. We're going to be looking at Diet Coke, regular Coke, and water. So when it comes to measuring the volume of a liquid, you're going to be best served by using a graduated cylinder. And measuring the mass, you can use something like a triple beam balance, or in class we just use electronic scales to save a little bit of time. Once you've got the mass and the volume, you can calculate the density using density is equal to mass over volume. And you can just repeat this calculation, or this whole procedure really, for the other liquids. So in class we had students come up to help me out with taking the mass and volume measurements of Coke, Diet Coke, and water. And here's some sample data. I'm guessing you don't have triple beam balances and graduated cylinders at home. So we've got the mass for all three, the volume for all three. We're also got the accepted values here. So these are literature values of what the, for lack of a better word, right density of Coke, Diet Coke, and water should be. And if you look at the numbers, the accepted value supports the observation that we made in class. Water has a density just about 1 gram per milliliter. Diet Coke is a little bit under that, and Coke is greater than that. So the Coke is going to sink, the Diet Coke will float, and water is what we're just using to separate the two. For the purpose of this tutorial, I'm going to focus in on the Diet Coke information. So I've got my mass, my volume, I've got the accepted value, and hopefully based on the blanks that are left here, you can conclude that we need to figure out the density and ultimately calculate the percent error. We use the percent error to gauge how good our measurements were. All right, so already took care of this, density and percent error. In my class, I really want you to show the work. Please don't just come to me with a number with a box around it, and that's your final answer. If it's right, that's great, you figured it out, but if it's wrong, I can't tell you where you went wrong because I have no idea what you did. So when I say show your work in class, there are 3 specific things that I'm looking for. First off, give me the formula. This is going to communicate to me how you plan on solving the problem, and it usually prevents students from making a lot of careless mistakes when they get to step 2, where they substitute in the numbers. I would prefer if you substituted with units, but if they're not there, I can live with it. Finally, you should be able to calculate the answer and make sure that you have appropriate units there. That last step, you absolutely have to show your units. Again, we can let it slide if they're not there in your substitution step. So let's go ahead and try to figure this out. So we know that it's density and percent error. So let's start off with density. Density is equal to mass divided by volume. If you look at the data that you copied down, the mass of our Diet Coke sample was 55.23 grams, and the volume was 51.0 milliliters. You can plug that into a calculator. No need to do that, in your head or by hand, and you end up with 1.08 grams per milliliter. And I like to put a box around it just to make it a little easier to see. Actually, just lost that one. There we go. That looks a little bit better. So based on the the measurements that we made in class, you get a calculated value of 1.08 grams per milliliter as the density of Diet Coke. Now that's not the actual density. So something didn't work out quite right with our measurements. Not the end of the world. You don't have to be perfect. We do need to calculate a percent error. Percent error is equal to the measured value, So for us, the 1.08 grams per milliliter minus the accepted value divided by the accepted value multiplied by 100. Feel free to use abbreviations when you go to write your formulas. Just make sure they make sense. All right, so I've got percent error, my measured value, 1.08, minus my accepted value, 0.997, divided by 0.997, and finally all of that times 100. In reality, there are some rules about how many digits you can have in an answer. We're going to cover those later this semester as we get a little bit more heavy into the math. For the time being, we'll just use the rule of please be reasonable. Do not give me every single digit that is generated by your calculator. So as I go through and I do the math, I take my 1.08, subtract out 0.997, and then divide that answer by 0.997 and multiply by 100. You should come up with about 8.3% error. All right, so not terrible, but definitely not great. To finish up today's lesson, what I'd like you to do is to summarize the results of the experiment. Go through, get a little bit of extra practice in, and see if you can find the density of the other liquids. Really, you've got the data, and the calculations are pretty quick. Do your results contradict your observation? Use the data to explain. Again, we saw the Coke sinking and the Diet Coke floating, and we've already just looked. The Diet Coke data does not support the observation that was made. And this last one is usually difficult for students to figure out, even in the advanced chemistry lab that we teach here. What is one potential source of error in the lab? When we say do not cite human error, that means we're not going to say that the person who was measuring the volume, for example, didn't use the graduated cylinder correctly. And this one's going to be especially difficult for those of you who are following along at home, as you did not actually conduct this experiment, you just got the data. But do your best, try to figure it out, and we'll be using the percent error formula a lot this semester, again, to evaluate how good your data and your results actually are.